Now we can go back and try to understand this strange behavior of photons and electrons a little bit more closely by trying to understand this proposition which says the electron either went through slit 1 or it went through slit 2. So to try to test this proposition, what we can do is we can run this experiment again with electrons, but now we'll try to detect which slit it went through. So what we can do is put a little source of light here, across slit 1 or across each of the slits, so that when the electron is going through the slit, the light actually bounces off of it and we get to see that the electron went by. So now what we'd imagine is not only are we going to get the interference pattern, but we're also going to actually detect what actually happened, whether this proposition that the electron went through either slit 1 or through slit 2. So when you actually do this experiment, what you realize is that in fact, and that it didn't go through both slits. And in fact, what you realize is, the result of this experiment does show you that every time you see the electron go past through slit 1, in fact, it doesn't go through slit 2. Every time you measure it as going through slit 2, it doesn't go through slit 1. But on the other hand, when you do the experiment this way, the count at this detector suddenly changes. You no longer see this interference pattern, but instead you see this pattern we saw with bullets. So this is a very strange thing. As long as you don't try to see which slit the electron went through, then you get the interference pattern. But if you try to see which slit it went through, to confirm this, confirm this hypothesis that the electron either went through slit 1 or through slit 2, well then you do actually detect that it went through either one or the other, but now the interference pattern disappears. Of course, you can turn down the intensity of light here by these two slits to make sure that you try not to disturb the electron as it's going through. And as you turn down the intensity, what you end up getting is some combination of this interference pattern and the straight addition. And in fact, the extent of this combination you get is exactly proportional to what fraction of the electrons you are able to detect at the slit 1 or slit 2. So nature perfectly hides her tracks. So if you try to measure which slit the electron went through, then the interference pattern disappears. If you try to detect only a little bit, then the interference pattern disappears a little bit, exactly when you actually do the detection. Okay, so let's summarize what we've learned about quantum mechanics. First thing we've learned is, in quantum mechanics, measurement outcomes are probabilistic. So where the electron or photon ends up, to detect it, you have to do a measurement, and the measurement is inherently a probabilistic process. Second thing, you cannot measure without disturbing the system. Whenever you make a measurement, you can make the measurement as subtle as you want, but you'll still disturb the system. The third thing we learned is that elementary particles behave in a very strange way. They behave like no classical entities that we have seen. They behave neither like particles nor like waves. but they behave in a completely strange way. Some of their characteristics seem as though they are like characteristics of particles. They behave like bullets. Other characteristics are those of waves. But really they behave like some funny combination of the two, which is like neither of the two at all. A fourth thing is that when we do this experiment, we can say that there's a moment when the electron leaves the source, the electron gun. And then from then on, we cannot really say what path the electron took, or whether it took multiple paths at the same time to arrive at the point X. And so we really cannot say what the trajectory of this electron is. So what quantum mechanics allows us to do is we start the experiment, it happens quantumly, and as soon as we look, as soon as we measure, that disturbs the system, and that gives us the outcome of the experiment. So there's this black box nature to a quantum experiment, where we start the experiment with this source of electrons, and then something happens, and then we do a measurement, and we see the outcome that the electron ended up at the point X. But in the middle here, we cannot really say what happened. And what the formalism tells us is that if we had a double slit here, then the electron has some amplitude A1 with which it goes through slit 1 and ends up at X, some amplitude A2 with which it goes through slit 2 and ends up at X, and the amplitude with which it ends up at X is A1 of X plus A2 of X, and the probability of detecting it there is the square of this amplitude. Okay, so that's the strange behavior of quantum particles. And okay, so starting next time, we'll start from scratch and talk about quantum bits and the basic axioms of quantum mechanics.